everyone, welcome back to another Math Notes video. Today we're going to be talking about rewriting radical expressions, which is a topic that came up in class the other day. And I got a lot of confused looks, so I'm glad we're going to get a chance to sort of review it and practice some more with it. This is section 2.2.1, by the way. Okay, so radicals, otherwise known as sort of square roots. But technically could be any roots, but today we're going to be talking about square roots, okay? Before calculators were readily available, people found it convenient to rewrite square root expressions in a simplest form or simplified form to make it easier to perform calculations, combine and compare them. A square root is simplified when there are no more perfect square factors, square numbers such as 4, 25, and 81 underneath the radical sign. Okay, well, let's figure out what that means, okay? So here's our first example. Example, square root of 72 can be rewritten in two different ways here. The first one, we could take the 72 and we could split it into square root of 9 times square root of 8. Okay, how do we know 9 and 8? Well, 9 times 8 equals 72. So we can split that from square root of 72 into square root of 9 times square root of 8. Well, the square root of 9 is now a perfect square, which is 3. And if I further break down the square root of 8 into the square root of 4 times the square root of 2, I have another perfect square, which is that square root 4. So now I have 3 times 2 times the square root of 2, which is 6 times the square root of 2. Now if you have a calculator handy and you want to double check your work at any time, modern calculators make this easy. We take the square root of 72 and we realize that that is approximately equal to 8.485. And if we take 6 times the square root of 2, which is, you should do this in your calculator to make sure you know how to do it. A lot of students run into errors just keying this in and getting the wrong answer. You should get 8.485 for this as well, which makes sense because they were just rewriting square root of 72 in a different form as 6 times the square root of 2. So another way to think about this, if you noticed that we could rewrite 72 as the square root of 36 times the square root of 2, because 36 times 2 equals 72, then you know right away that the square root of 36 is 6, and the square root of 2 is left over. Okay. I'm going to do a little aside here real fast and just kind of show you a different way that I've thought about this before. One way, if you're not really sure how to break these down, is start by doing a factor tree, which you guys did back in middle school. So if I know 72, it ends in an even number, so I can multiply it by 2. I know that's equal to 2 times 36. And again, let's assume I didn't notice that 36 was a perfect square, so that's 2 times 18. 18 is 2 times 9. 9 is 3 times 3. Alright? So when I'm looking at perfect squares, one way to think about it is it's a pair of numbers underneath the radical. So I have a pair of 2's and a pair of 3's. The pairs can come out of the radical, so that would be a 2 outside, a 3 outside, and the single guys have to stay inside, which is 2. So we're looking for pairs. They come out, singles stay in, so we have 2 times 3 times 2, which is 6 times the square root of 2. Just a slightly different way of doing the same thing. All right, let's look at another example here. Example, square root of 72 plus the square root of 18. Well, so your instinct might be to go straight for the calculator, but we can actually get an exact answer if we simplify these. So square root of 72 we just did. We know that simplifies to 6 times the square root of 2. And we want to simplify the square root of 18. So off to the side here we're going to say square root of 18 breaks down to the square root of 9 times the square root of 2, because 9 times 2 is 18. The square root of 9 is 3. Square root of 2 is an irrational number, so it's 3 times square root of 2, which we have right here. Okay, we're going to treat this these numbers underneath the radical basically the same way we would as a variable. So if we had 6x plus 3x, then our answer here would be 9x, and in this case our x is equal to the square root of 2, so it's 9 square root 2. Alright, so when they have the same number underneath the radicals, we can just add the coefficients like that. Okay. Let's look at one more example. We're going to look at something called rationalizing the denominator. I'll write that out here. Rationalizing denominators. All right, let's read the first paragraph there. It is difficult to estimate the value of a number with a radical in the denominator, and it is also difficult to combine it with or compare it to other numbers. For these reasons, it's sometimes helpful to rationalize the denominator so that no radical remains in the denominator. So there's that phrase again. All right, so here's our example. 10 divided by the square root of 2. We're going to get rid of the square root of 2 in the denominator on the bottom. I'm going to jump right over here to the example. To do that, we're going to multiply the top and the bottom of that fraction by square root of 2. So we have square root of 2 over 2. Now, I am allowed to do that because square root of 2 over 2 equals 1. So we're really just multiplying it by 1, but in a sneaky way. So I multiply across the fraction. I get 10 times square root of 2 is 10 square root of 2. And then I get, on the bottom, square root of 2 times square root of 2 is the square root of 4, which is just 2. So I'm left with 10 square root 2 divided by 2. I can simplify those numbers outside the radical. 10 divided by 2 is 5. So this simplifies to 5 times the square root of 2. All right. So I've got a couple of things for you to practice on the next page. Give those your best shot, guys. Simplify all of these square roots, and we'll talk about it tomorrow.